Welcome to the deep dive. Today we're tackling a really fascinating set of source materials. They detail something called the pathogen core.
Yeah, it's quite something. Not your typical malware.
Definitely not. It's described as a self-replicating entity, and the really strange part, its whole logic seems engineered around PHI, the golden ratio.
Exactly, that mathematical constant, 1 plus sqrt 5, it's not just like a setting, it is the system's engine.
So it actually uses PHI directly.
Oh yeah, right from the start. For YIT, that's system initialization, and it uses it constantly to generate MIKE's unique random data, basically. Makes it seem less predictable.
Okay, so this golden engine. Let's unpack that a bit. You mentioned initialization, random data. What else? How deep does it go?
It goes right to the core state. The system has this internal vector. Think of it like its operational signature or current status.
Yeah.
And PHI is constantly modulating that vector.
Modulating how?
Well, there's the Litherian, which acts as the sort of system brain. It evolves the vector using things like resonance cycles, uses Fourier transforms, apparently, to keep the state coherent.
Okay.
And crucially, it uses the Brownian updates, Brownian motion logic, to introduce, well, mathematical randomness, unpredictability into that core state.
Wow. And I saw mentions of PHI and command functions too, like permuted dragon.
Mm-hmm. That uses PHI cubed to scramble and encode command strings, ensures everything carries that specific mathematical signature derived from PHI. It's deeply integrated.
So if the identity is PHI, does that influence how it replicates? I saw terms like phi-replicator and worm-for-shell.drawcopy.
It does, yeah. It leans into that fractal geometry idea, linked to PHI and Fibonacci. It creates copies, copypathogen.py, sequentially.
But it doesn't just replicate endlessly.
No, and that's interesting. There's a hard limit. Fractal depth is set to 7. It won't create more than 7 nested copies.
Why limit it? Seems counterintuitive for something trying to spread.
Well, the thinking seems to be stealth. The golden ratio, Fibonacci, fractals, they can grow exponentially. Capping it at 7 might be an artificial limit to avoid, uncontrolled spreading. That would be really noisy and obvious.
Smart. Keep it contained but active. And this structure is managed.
Yeah, by the Dragon Queen. It oversees all the nodes in the swarm, issues commands that they call them decrees, coordinates the whole thing, while the Lyrian handles the internal state evolution.
Okay, so we have this limited, structured swarm. How does it actually get onto new systems? The propagation methods looked pretty robust.
They are. The network scanner is quite thorough. It does a deep scan across, 9 specific subnet ranges.
Not just the usual home network stuff?
No, it covers the 1i2.168.x and 10 data.x ranges, sure. But also link local 169.254.0.x, and it targets 7 common ports, 22, 80, 443, 80, 80, the usual suspects for finding services.
All right, so it finds potential targets, then the SS agent tries to deploy.
Right, and this is where it gets really clever, or maybe flawed, depending on how you look at it.
How?
Stage 1 uses credentials generated mathematically from PHI and the current time, the gencreds function.
Okay, that fits the theme. Highly advanced.
So if that fails, stage 2 just tries a fallback list. Really basic stuff, admin, Pyrosberry.
Wait, really? After all that complex PHI stuff, it just tries admin? Doesn't that seem like a huge step down, a vulnerability?
It does seem odd, right? But perhaps it's about pragmatism. Fault tolerance versus, mathematical purity. Maybe the PHI credentials need perfect time sync or something on the target.
So the fallback is a just in case it needs to land something.
That seems to be the idea. Sacrifice elegance for a higher chance of success. And success means persistence. It uploads via SFTP and sets up a cron job to run every 5 minutes. It wants to stick around.
Persistent, definitely. And once it's on multiple machines, how do they talk? The swarm communicator.
Exactly. It builds a mesh network. The handshake involves sending a secure JSON message. Contains the node ID and, crucially, that current vector state driven by PHI.
So they sync up their internal states.
And communication seems reliable. Broadcast commands, like asyncio vector, and waits for an ACK confirmation from nodes. No shouting into the void.
And there's another layer, the advanced network orchestrator.
Right. It seems to manage the overall tempo, limits deployment attempts to just the top 3 discovered hosts per cycle.
Ah, another stealth measure. Avoid flooding the network.
Probably. Keeps it aggressive, but maybe below the threshold for automated network alarms. It's all coordinated by this enhanced Ruth-Pathos structure.
It's quite the design, combining fundamental math with, modern resilient networking. Abstract logic meets practical deployment.
It really is. Which leaves us with a pretty interesting final thought for you listening.
Go on.
Well, If security, propagation, the core logic itself, if it's rooted not just in code someone wrote, but in dynamic fundamental constants like PHI, what new challenges does that pose?
Yeah.
How do you defend against logic dictated essentially by the mathematical fabric of the universe itself?
That's a really mind-bending question, defending against math itself. Lots to think about there.
Welcome to the Deep Dive. Today, we're tackling something pretty fascinating. It's this complex system called the pathogen core.
Yeah, it is.
And our mission really is to kind of pull apart how this thing works. It's self-replicating, driven by some pretty advanced math.
That's the hook, isn't it? The whole system, its like core identity and how it operates, it all comes back to PHI, the golden ratio.
The golden ratio. Okay. So 1 plus squared 5, 2, that specific number.
Exactly. It's not just decorative. It's baked right into the engine of the whole thing. It dictates propagation, keeps it unpredictable.
Right. Okay. So let's unpack that golden engine idea. How deep does the PHI integration actually go? I mean, I see it right at the start, initializing things.
Oh, absolutely. It's used for the initial state, but also for generating like core random data streams, bytes. Even drives this specialized permutation function they call permutadragon.
Permutadragon. Okay. And using PHI for randomness.
Yeah.
What's the advantage there? Why not just standard pseudo-random stuff?
Well, the advantage is in the nonlinearity. Because PHI is irrational, using it in that permutation makes the scrambling pattern fundamentally nonlinear, much harder to reverse engineer or spot patterns in, resists standard tools.
Okay, I see. And you mentioned the state. This isn't static, right? You said it keeps changing. Sounds like it's more active than typical malware just sitting there.
Way more active. It maintains this internal vector, its core state, right? And that vector is constantly being modulated. You've got these resonant cycles, resonance, and state updates using Brownian motion logic, a Brownian.
Both using PHI. Yeah.
Both driven by PHI, yeah. There's this component, the Letherian, that acts like the system brain. It's constantly evolving that vector state. So mathematically, the pathogen basically never sits still.
That dynamic nature, it seems to carry over into replication too. We see the file replicator making copies, like a fractal.
Kind of, yeah. It creates copies, copypathogen.py, sequentially. But there's this interesting limit.
Right, the fractal depth of 7. Why? Why stop at 7 copies deep? Seems odd for something designed to spread.
Well, it prevents that runaway exponential growth, the kind that screams infection on network monitoring. It's controlled.
Suggests some kind of intelligence or strategy behind it.
Exactly. And it points to the hierarchy. You've got the Dragon Queen coordinating the nodes, issuing these decrees.
Broadcast, basically.
Yeah, broadcast to the swarm. It's a structure built for stealth, for long-term presence, not just a smash and grab.
Okay, let's shift to how it actually gets onto new systems. Network propagation. It mentions a deep scan. How deep are we talking?
It's pretty comprehensive. The network scanner doesn't just ping 1 or 2 places. It hits like 9 specific private subnet ranges. Your typical 192.168, 10 dots, even link local addresses.
So thorough internal scanning and ports.
Targets 7 common ones, 22, 80, 443, 8080. The usual suspects for finding services it might exploit. Really trying to map out the internal network.
And then the deployment. This is where PHI comes back in a big way, right? The SS agent.
Yes. It first tries to get in using credentials generated mathematically, on the fly.
Using PHI and the current time, gen grids. Okay, wait. If they're generated like that, couldn't you eventually figure out the pattern?
That's the tricky part. Because it uses PHI and time, the possible keys are, well, practically infinite, and each one is only valid for a very short window. It's designed to make standard dictionary or brute force attacks almost useless.
So that complex method is plan A.
Right. Only if that fails does it resort to, admin, purist berry, the common stuff. That's the backup plan.
Clever. Okay, so it gets in, then what? Persistence seems key here.
Immediately, it uploads the payload using SFTP, then locks itself in, sets up a cron job.
The scheduler task.
Exactly. To rerun the pathogen file every 5 minutes just keeps ensuring it's running. That persistence is vital for the swarm communication.
Right. Building that mesh network. How does the swarm communicator actually connect the nodes?
It uses a handshake process, send a secure JSON message containing the node's ID, and crucially, that PHI-driven vector state we talked about earlier.
Sharing its current mathematical state.
Yeah, so nodes are synchronized, and the communication seems reliable too. For important commands like swinc vector, it waits for an ACK.
An acknowledgement. Confirms the message got through.
Precisely. Ensures commands are received across the swarm.
And even the rate of spread is controlled. The advanced network orchestrator? it limits deployment.
Yeah, to just the top 3 most promising hosts it finds in each scanning cycle. Again, avoiding too much noise, avoiding detection, controlled expansion.
So putting it all together,
Mm-hmm.
what we're looking at is this really elegant fusion, a fundamental constant from mathematics, PHI, blended with modern, robust networking.
It really is. Fault-tolerant, self-regulating, dynamic, fractal even, all orchestrated by that mathematical core via the enhanced root of pathos. Quite the system.
A masterclass, like you said, in mixing pure math with practical, albeit malicious operations. And, that leaves us with a final thought for you, the listener. If systems like this start rooting their security, their propagation, not just in lines of code, but in these dynamic, fundamental constants, like the golden ratio, what does that mean for defense? How do you defend against logic that mirrors patterns found in the natural world itself?
That is a challenging question. Defending against math itself.
Something to think about. Maybe next time you see a spiral galaxy or seeds in a sunflower. Welcome to the Deep Dive. Today, we're really digging into the source code of this autonomous system, the pathogen core.
Yeah, it's quite something.
We've got the code here, and it shows, well, something pretty unique. The whole system, how it makes passwords, how it spreads. It seems engineered around the golden ratio.
That's exactly it. And this isn't just, giving things fancy names. The actual algorithms, the core functions, they use that constant 1 plus sqrt 5.
From nature, basically.
Right. And they're using it to drive things that you'd normally expect to be, well, purely digital, predictable. Our mission today is figuring out why. Why build potentially a malicious system using a geometric constant as its engine for chaos.
Okay, let's start right there with the map. How does this golden ratio, which we usually associate with like shells and flowers, how does that generate randomness for security stuff?
Well, it's clever, actually. It uses I to seed entropy. There's this function, myBytes, that mixes I with the current time to generate random bytes. And because ID is irrational, nonlinear, the output becomes incredibly hard to predict. It gives the system a really dynamic, sort of chaotic starting point for everything else.
And that chaos gets weaponized straight away, doesn't it?
Yeah.
It feeds right into forging credentials, making its own passwords. Gencryds, I think it was called.
Exactly. It takes those I-seeded random bytes, hashes them using SHA-3256, and then, this is the interesting part, it passes that hash to something called permuted dragon.
The dragon permutation. Sounds dramatic.
It kind of is. It uses powers of A and even sign functions to essentially shuffle and permute the hash output into usable credentials.
What comes out?
Unique usernames, alphanumeric, up to 8 characters, and passwords, 12 characters long, all mathematically derived.
Huh. So the whole system is designed to be dynamic, chaotic. We see that elsewhere too, right? With functions like a resonance and a Brownian affecting its state.
Yeah, that seems to be about keeping its internal state fluid. It's never static. A resonance looks at frequencies, maybe checking its own operational vibe, scaled by A, of course.
Right.
And a Brownian applies a random walk, again using A, to its internal vectors. It seems designed to constantly shift, making it harder to fingerprint or analyze reliably.
Always moving. And speaking of moving, let's talk replication. It copies itself, makes files like copy pathogen dy, but there's that weird limit.
Ah, yes, the fractal depth. It's hard-coded to 7.
7 generations deep, and that's it.
Seems so. It suggests a built-in break, maybe to avoid detection from runaway replication, maybe resource control, maybe something else entirely, but it's a fractal limit, which feels deliberate given the A connection, like a natural constraint.
So once it's done its limited copying, it starts hunting. The network scanning looks really thorough, 9 subnets, 7 ports.
And look at the subnets it targets. Of course, you've got the usual suspects, 192.168.10.0, but look here.
169.254. So they usually just link local, right?
Oh, yeah.
Stuff devices use when they can't get a proper IP.
Exactly. But these days, that range is heavily used by container systems, Docker, Kubernetes, cloud environments. Targeting it explicitly means this thing is built to jump between containers, cloud workloads, not just old school servers.
Okay. That's insightful. But here's where I get a bit confused. The deployment, the SS agent. It has this 2-stage approach. First, it tries those super complex A-generated passwords.
Right, the ones derived from permuted dragon.
But if they don't work, it just falls back to trying admin with password admin or Pi and Raspberry. Why bother with all the fancy math if you're just going to try the defaults anyway? It seems like a contradiction.
It does seem odd at first glance, but think about it from an efficiency perspective. The generated credentials offer maybe stealth and uniqueness, a way in on potentially well-configured systems if it gets lucky, but the system prioritizes success. The fallback to common default credentials like admin, or praspberry hits the low-hanging fruit. It covers the vast majority of poorly secured devices out there. It's like intelligent brute force meets mathematical finesse. Get in however you can.
Okay, that makes more sense. Maximize the chances. And once it's in via SSH, it digs in deep.
Oh, yeah. It uploads the payload using SFTP, changes permissions, runs itself in the background using no-hup so it persists even if the connection drops, and sets up a cron job to make sure it restarts. Standard persistence.
And there's something managing all these deployed copies, right? A central command.
That appears to be the Dragon Queen class. It manages the swarm node instances, the individual infections, and issues decrees using a broadcast mechanism. So it maintains central control over this decentralized, mathematically driven swarm.
So wrapping this up, what's the big picture here? The core thing is this deep link between abstract math, the golden ratio, and concrete malicious actions like generating credentials and controlled fractal replication.
Exactly. It's not just math for math's sake. It's using the inherent properties of a natural constant, potentially for its nonlinearity, its unpredictability, to build a system that evolves or spreads in a way that's maybe fundamentally different from purely digital logic.
Which leaves us with a pretty interesting final thought.
Yeah. What does it really mean? What are the implications when we start seeing these fundamental constants of nature being used as the building blocks for digital autonomy, for network operations, maybe even for malicious actions? It's a strange intersection. Okay, let's dive into this. We've got this really complex design document. Feels more like source code, honestly.
It practically is, and it describes this self-replicating network thing.
Right, the docs call it the pathogen core, or sometimes root of pathos. Bit dramatic, maybe?
Maybe, but the names hint at the core idea.
Yeah.
Our job, though, is to figure out what really sets this apart, you know?
Exactly. And the hook seems to be math, specifically the golden ratio, phi.
Precisely. It's not just decoration. Phi, like the actual number, one source sqrt 5.2, is fundamental. It dictates almost everything. It's the core engine.
So it's using phi for randomness. I saw functions like bbytes for entropy, seedforge. How does using a fixed number like phi create randomness? Seems counterintuitive.
Well, it's more like pseudo-randomness, but with a very specific mathematical signature. It looks chaotic from the outside, maybe.
But internally?
Internally, it's deterministic, predictable if you know the math.
Yeah.
It seems designed for a kind of structured chaos, not just pure random noise.
Okay, structured chaos. And this feeds into its internal state, the vectors.
Yeah, that's where it gets pretty heavy. There's the resonance.
I saw that. Uses fast Fourier transform, FFT.
Right, FFT. But applied to frequencies that are scaled by phi, this generates the system's core vector state. It's sort of identity.
An identity that keeps changing.
Constantly. That's the Brownian function. It nudges the vectors, keeps them evolving within their dimensions, using math related to Brownian motion, like particles jiggling around.
So the whole internal structure, this Lytherian they call it, is always shifting, but according to these phi-based rules. Makes sense.
It ensures it's complex, unique, always in flux, but stable in its own mathematical way.
Oh, okay.
Yep.
Cool, internal math. But how does it get out? How does it spread across the network?
Ah, right, propagation. It uses something called phi replicator.
Self-copying, yeah. With wormfish shell.drop copy.
Exactly. It's designed for fractal growth, branching out. But here's a key detail you spotted.
The fractal depth, limited to 7.
Right, only 7 generations deep.
Right.
Why?
Good question. Avoid detection. Limit runaway spread.
Could be both. It suggests control. It's not just mindless replication. It stops itself. Maybe preserves resources, stays under the radar compared to something that just goes wild.
Makes sense. Controlled spread. But the scanning part seems less controlled.
Oh, definitely not subtle there. The network scanner is aggressive.
Deep scan subnets.
Yeah.
It hits all the common private IP ranges, doesn't it? 192.168, 10.172.16.
Yep, the works. Home networks, corporate ranges. And it targets common ports 22 for SSH, 80 and 443 for web, 8080 for proxies. Pretty standard targets, but scan deeply.
So find everything, infect selectively. And how is this managed? You mentioned a kind of hive structure.
Yeah, there's a Dragon Queen entity acting as the central controller.
Dragon Queen.
It manages the individual swarm nodes. And communications handled by a swarm communicator.
Yeah.
Broadcast commands, crucial stuff like sys1 and cvector to keep everyone aligned.
And it needs confirmation, like read receipts.
Exactly. Delivery confirmation required from every node.
Yeah.
Tight control.
Which leads us to deployment, how it actually gets onto a new machine via SSH. This is where that contradiction comes in.
It really is stark. Managed by the SS agent. Two main strategies.
First one is deploy with generated creds, using phi again.
Yes. It uses GenCreds, which incorporates phi to create randomized usernames and passwords. Sophisticated, mathematical, keeps with the theme.
Okay, clever. But maybe not always effective against real-world systems.
Apparently not, because the fallback is, well, it's basic.
The deploy with common creds function.
And it just tries a hard-coded list. Things like admin, root,
Pi, Raspberry 2, I saw. Just the most common default passwords.
Exactly. After all that complex phi mathematics, tries admin. It's quite the mix.
So high math meets low-hanging fruit, if either works.
Then it executes the final sequence, upload the payload, and crucially, set up persistence.
The cron job, running every 5 minutes.
Yep. Embeds itself, makes sure it stays running and checks back in. Locks itself down.
So wrapping this up, what we're looking at is a distributed system, a swarm, that uses deep math, the golden ratio, for its internal logic, its randomness, even for generating some credentials.
Right. But it pairs that complexity with really pragmatic, common brute force techniques to actually spread.
It's that blend. The mathematical elegance inside and the basic attack methods outside.
It makes you think, doesn't it? Using a fundamental constant like phi to generate entropy, it suggests wanting behavior that's predictable internally but looks random externally.
So the final thought for you listening. If something as basic and universal as a mathematical constant can be woven into code like this, used for controlling network behavior and creating seemingly random secrets?
What does that really imply about the security assumptions we make? Especially for systems relying on what we think is truly unpredictable randomness.
Yeah.
It's something to chew on.
Welcome back to the deep dive. Today we're digging into a technical audit, specifically the pathogen distributed swarm system.
Right. And the mission really is to understand why this system, which claims to be quantum resistant, is actually critically compromised right now.
Despite all the complex architecture they talk about.
Exactly. The synthesis here is, well, it's pretty stark. High-level math concepts, yes, but undermined by basic security flaws, resource issues, even simple coding errors.
So serious problems needing immediate P1 fixes.
Absolutely. P1 level, no question.
Okay, let's start with maybe the most ironic part, the quantum-resistant PRNG. This thing uses constants like phi, e. Sounds impressive.
That sounds impressive, yeah. It's meant to generate entropy using these constants and chaotic transformations.
So how does something that complex just fail?
It's almost unbelievable, really. It fails because of a basic typo, a variable casing defect.
Wait, a typo?
Yes, the code sets up the initial state using an uppercase variable, x, but then inside the loop where the generation is supposed to happen, it tries to read lowercase x.
So it just crashes. A name error.
Precisely. A simple name error means the entire complex mathematical sequence, the core of the PRNG, it never even runs.
That's not even a security bug. That's just a P2 coding blunder stopping the whole thing cold.
It is. But even if you fix that typo, there's a deeper problem.
Oh.
The seed state, the starting point for the math, it's never updated.
What does that mean in practice?
It means you get the exact same 2024-byte sequence of mathematical inputs every single time the buffer needs refilling. Highly predictable. Completely deterministic, actually.
So it fails basic randomness standards like the NIST ones?
Instantly. Fails SB 890B. The output has to be unpredictable statistically. This is not even close.
Okay, so the PRNG is fundamentally broken, typo or not. Let's talk P1 critical issues. The audit highlights the swarm node handshake protocol.
Yeah, that's a major one. It's essentially broken. It's missing basic security elements.
Like what?
Nonces, for one. And HMAC verification.
Explain that a bit. Why are those crucial?
Okay, so a nonce is like a one-time code. It proves the connection request is fresh, right now, stopping someone from just recording and replaying an old valid connection request later. That's a replay attack.
And the HMAC.
That verifies message integrity. It proves the message hasn't been tampered with in transit. Without both, an attacker can basically just spoof a connection, record a real one, play it back. Trivial.
Wow. Okay, another P1 mentioned is resource exhaustion, the secure connection manager.
Ah, yes. The connection pruning logic is flawed. It's supposed to remove the oldest, maybe unresponsive connections to free up resources, right?
That makes sense.
But instead of checking connection metadata, like, the actual age or last activity time, it uses next iter on the connection dictionary.
What does that do?
It just grabs, well, effectively an arbitrary connection based on internal dictionary ordering. Often the first one added, not the oldest or stalest.
So good connections might get dropped while bad, unresponsive ones just hang around.
Exactly. They stay active indefinitely, consuming system resources like file descriptors until the whole node just chokes, runs out of handles.
And the last big one, incomplete components, the secure deployment agent being a stub.
Yeah, that's deeply concerning. Critical security functions like signature verification for code payloads, sandboxing, they're just marked as to do. They're not implemented, meaning the system can basically be told to execute unverified, potentially malicious code. There's no check, no safety net. It violates basic secure design principles.
Okay, so remediation. Beyond fixing the typo and the logic bugs, what are the immediate security steps?
For the handshake, you absolutely need a proper challenge response mechanism. Cryptographically secure, use nonces, timestamps, maybe session keys. Standard stuff, really.
And for resilience, the audit mentioned issues with error retries.
Right. The current system uses a simple fixed delay for retries. If there's a network glitch and many nodes disconnect, they all try to reconnect at the exact same moment.
The thundering herd problem. It can craft the network again.
Precisely. You need exponential backoff. Wait longer each time you fail, and add jitter a small random variation to the delay.
So something like asyncio.sleep2 retry plus random.uniform 01.
Exactly like that. It staggers the reconnection attempts, prevents the stampede, and gives the system a chance to actually recover gracefully from outages.
So summing up, if a pathogen needs these P1 and P2 fixes urgently, basic coding hygiene, standard security protocols, forget quantum resistant for now.
Absolutely. Get the fundamentals right first. Fix the bugs, harden the protocols.
And then worry about the advanced stuff.
And even then, you can't just claim it. That PRNG, once fixed, it needs rigorous testing, statistical analysis. Use suites like DieHarder or Test201 to prove its output is actually random and unpredictable over long streams. The claims need validation.
It leaves you thinking, doesn't it? A system built on, the golden ratio, brought down by a lowercase x, makes you wonder how much complexity we should trust versus how much basic, careful auditing we really need. Something for you to consider.
Welcome to the deep dive. Today, we're tackling something pretty intense. It's a code base called ffpathogen.
Yeah, and this isn't your standard piece of malware. The documentation calls it an expert-level prototype.
Right, for an asynchronous network worm.
Mm.
And it has this very weird, highly mathematical playstyle.
Exactly. And that's really our mission for this deep dive, to get our heads around this strange design philosophy. It kind of mixes real malice with this almost beautiful mathematical structure.
It relies heavily on universal constants, doesn't it? Like pi.
Pi, the golden ratio phi, Euler's number dollar. They're baked in for survival, for resilience. It's fascinating.
Okay, so architecture first. It's built on Python's asyncio. Now, we don't need a coding lesson, but what does that tell you?
It tells you it's built for speed and scale, like massive scale, handling tons of connections at once, non-blocking. It's designed to be fast.
To spread quickly and manage itself across potentially thousands of nodes simultaneously.
Right. Which brings us to the math part, what the docs call the golden revelation, this chaotic trinity of constants. Phi, pi, and etchy.
Okay, hold on. Why those specific numbers?
Yeah.
Seems almost academic. Why not just use standard system randomness for, say, security tokens?
Well, that seems to be the point. They feed these into their custom random number generator, the quantum-resistant PRNG. They even call it the Genesis engine.
Genesis engine, huh? Okay.
Yeah, and they're not actually looking for true randomness. They want what they call deterministic randomness.
Meaning it looks random, but is it?
Exactly. They use these constants in iterative steps transformations to generate number sequences that are incredibly complex, nonlinear, but technically predictable if you knew the starting seed.
Okay, so what's the advantage for the worm?
Predictability internally. If every infected node can generate the same complex sequence from the same seed, they can verify each other. It's used for their internal C2 command and control tokens.
Ah, so they don't need to manage static keys, which could be found.
Precisely. It's dynamic authentication, though interestingly, they had to patch it. Yeah, they added mandatory state reseeding. After generating 724 numbers, the state has to be reset to ensure the sequences stay statistically independent, prevent prediction.
Okay, so that handles secure internal comms. But you mentioned scale, like a swarm. How does a swarm stay coordinated, keep a shared sense of what's happening?
Right, that's where the swarm soul concept comes in. It's really advanced stuff.
Go on.
There's a module called Cortex. It keeps this internal state, this reality matrix, basically capturing the system's history, its dynamics.
Like a shared memory for the whole worm network.
Sort of, yeah. And it's constantly updated using something called a temporal anchor. This involves Fourier transforms on system time, scaled by the golden ratio, phi.
Wow. So math creates this constantly evolving, verifiable, shared truth across all infected machines. The swarm soul.
That's the idea, a shared ontological state, as the docs put it.
Which must make it incredibly hard to disrupt. But what about detecting it? Forensics.
Well, that leads to temporal stealth. This is their main anti-forensics trick.
Okay, I saw mentions of PHI-based mathematical jitter. What does that actually do?
It messes with time. Basically, they add a variable delay to pretty much every operation. The delay is calculated using the golden ratio and the current system time.
How much delay are we talking?
It can add up to 15 seconds of unpredictable, chaotic jitter.
15 seconds. That's huge in network terms.
Exactly. It makes the worm's activity pulse completely irregular, standard time series analysis, looking for repeating patterns. It won't see this thing. It blends into background noise.
Clever and terrifying. So it spreads, stays hidden using this jitter. Where does it spread? And what's the final goal for persistence?
Propagation targets typical private network ranges, 192.168, 10 dot, whatever. It uses chaotically generated credentials. The algorithm's called Bermuda Dragon.
Okay.
And the ultimate persistence goal seems pretty standard, actually. Get its execution command deep into the target's cron tab file. Make sure it runs again after reboots.
But after all that complexity, the swarm soul, the jitter, what does it do? The sources talk about the destiny of absence.
Correct. And that's the final twist. Right now, ppathogen does. Nothing destructive. There's no damaging payload. Nothing obvious. It's defined purely as a stage 1 colonizer. Its only job is to spread, persist, stay hidden, and keep that swarm soul synchronized. Build the infrastructure.
So the lack of a destructive payload that's deliberate. It's not just unfinished.
Seems entirely deliberate. The whole system is built, poised, waiting. The documentation mentions receiving a final payload later, delivered via that synchronized C2 state. They call that the destiny of wrath.
So it builds a perfectly hidden, resilient global network, just waiting for the final command to presumably do something awful.
That appears to be the design.
It's quite something.
Yeah.
It's incredible effort to create external chaos, mathematical unpredictability for stealth, but internally, it needs absolute discipline, locks, semaphores, resource management, strict rules to keep itself from collapsing under its own complexity. So here's something to think about. What does it tell you when a system designed entirely for disruption and chaos absolutely requires rigid internal order just to survive? Something to mull over.
Okay, let's dig into this. We're doing a deep dive today on something called ppathogen core. It's an advanced network worm prototype, but it's definitely not standard stuff.
Not at all. The really interesting bit, the hook here, is how it mixes high-performance, code-like, asynchronous programming with some really abstract math.
Abstract math? You mean the golden ratio? That's pretty unusual.
Exactly. And it's not just for show. We're classifying this thing as a self-propagating network worm.
Or
independent, built for sticking around, persistence, and decentralized C2.
So less smash and grab, more long-term colonization.
Precisely. Stealth and survival seem to be the top priorities in its design, not, quick destruction.
Okay, so where does that stealth come from? The docs mention this, chaotic core.
Right, that's kind of its anti-forensic heart. It generates entropy using not just one, but three transcendental constants, pi and Euler's number E.
But why those? Why not just pull randomness from the operating system like normal?
Well, it's about avoiding predictability. Standard system entropy is good, but they built this quantum-resistant PRNG. It mixes fresh OS entropy with a chaotic map that's derived from those constants.
And that fixes a specific flaw.
Yeah, a critical one, actually. CWE 338. Basically, older prototypes had this issue where their random sequences would eventually repeat. Deterministic cycling. Using chaotic math helps prevent that non-repeating assurance.
Okay, that makes sense for the internal randomness, but how does it hide its activity from, say, a security analyst watching the network? You mentioned the jitter.
Exactly. That's the really clever bit for operational stealth. When the worm pauses between actions like scanning or trying to connect, it doesn't just wait a fixed time, say 5 seconds.
It does what instead?
It injects jitter into that delay. And that jitter is calculated using the golden ratio, so you get these non-integer, slightly chaotic variations in timing.
Ah, so any tool looking for a regular rhythmic pattern like a heartbeat won't find one.
Precisely. It scrambles its timing footprint, makes time series analysis much, much harder.
Okay, so its timing is hidden. Let's talk architecture. How does it handle actually breaking in? The analysis suggests it's, well, pretty well built.
Oh, definitely. This looks like professional development. For example, they've addressed common vulnerabilities like predictable temporary file paths, that whole TOU race condition thing.
Where you can guess the file name between creation and use.
Right. They neutralized that during remote deployment by using cryptographically secure random suffixes for any temporary files. It's just clean, disciplined coding.
But then there's this concept they call controlled aggression. If it's so sophisticated, why wouldn't it just go full blast, try to spread as fast as possible?
Because full blast is noisy. It triggers alarms immediately. This worm is smarter than that. It actually throttles itself.
Throttles itself? How?
Inside its network discovery engine, it uses what looks like an asyncio semaphore set to 20. So it strictly limits itself to only 20 concurrent outbound TCP connection attempts at any one time.
Only 20. That seems low.
It is low, intentionally. It prevents the worm from hogging system resources or creating that obvious high-volume scanning signature that network monitoring tools are built to catch. It's prioritizing stealth over speed, like a slow drip instead of a flood.
Okay, so a low and slow approach. How does it actually move laterally then? The vector is SSH, right?
Yes, asynchronous SSH, technically T1 tunnel 1.004, but it's not just brute forcing common passwords. It uses this really complex algorithm called permuted-dragon.
Permuted-dragon. What's that based on? Let me guess.
You got it. Rooted in chaotic powers of Filer that generates highly unpredictable, time-dependent credentials for each login attempt. The goal seems to be evading simple dictionary attack lockouts.
Wow. Okay, so chaotic timing dynamic credentials. This sounds really tough to stop with traditional tools.
It is, because the timing jitter bypasses time series analysis, and the credential forging bypasses simple signature or blacklist approaches. Your defense really has to be behavioral.
So what's the recommended countermeasure? What actually works?
The most effective thing. You have to shut down that SSH vector. The recommendation is clear. Enforce mandatory key-based authentication for all SSH services, everywhere.
Because if it can't use a password, the whole permuted-dragon credential forging thing is useless.
Exactly. It completely neutralizes that attack method. No password field, no attack.
Okay, but what about detecting it before it spreads? You mentioned it throttles itself. Can we use that?
Absolutely. That self-imposed limit, the 20 concurrent connections, that becomes its Achilles heel. We tune its stealth into a detection point.
Ow.
You implement security policies, specifically network flow monitoring, designed to spot that exact behavior. The recommendation is to flag any internal host that attempts more than 20 unique internal TCP connections within, say, a rolling 60-second window.
So you're basically setting a tripwire at its own speed limit.
Precisely. You use its own controlled aggression against it.
Okay, wrapping this up. What's the big picture here? The analysis mentions resilience, decentralized state synchronization.
Yeah, that's important. The different parts of the worm, the modules, seem to synchronize their state using complex methods like fractal Brownian motion. It means a whole swarm of these things could likely survive even if you find and kill individual infected nodes. It's built to be robust, decentralized.
Which leads us to a pretty challenging final thought for everyone listening.
Right. If sophisticated attackers are actively integrating things like pi and other nonlinear mathematical concepts into real-world cyber weapons, well, how much deeper does security need to go?
You mean we need to start integrating abstract math into our defenses just to keep up?
Maybe. You certainly can't fight these kinds of non-deterministic, chaotic threats using simple linear pattern matching anymore. It raises some big questions about the future of cybersecurity analysis.
Okay, let's dig into this. We're doing a deep dive today on something called pathogen core. It's an advanced network worm prototype, but it's definitely not standard stuff.
Not at all. The really interesting bit, the hook here, is how it mixes high-performance, code-like, asynchronous programming with some really abstract math.
Abstract math? You mean the golden ratio? That's pretty unusual.
Exactly. And it's not just for show. We're classifying this thing as a self-propagating network worm.
Oh, or...
Independent, built for sticking around, persistence, and decentralized C2.
So less smash and grab, more long-term colonization.
Precisely. Stealth and survival seem to be the top priorities in its design, not, quick destruction.
Okay, so where does that stealth come from? The docs mention this, chaotic core.
Right, that's kind of its anti-forensic heart. It generates entropy using not just one, but three transcendental constants, pi and Euler's number E.
Huh. But why those? Why not just pull randomness from the operating system like normal?
Well, it's about avoiding predictability. Standard system entropy is good, but they built this quantum-resistant PRNG. It mixes fresh OS entropy with a chaotic map that's derived from those constants.
And that fixes a specific flaw.
Yeah, a critical one, actually. CWE 338. Basically, older prototypes had this issue where their random sequences would eventually repeat. Deterministic cycling. Using chaotic math helps prevent that non-repeating assurance.
Okay, that makes sense for the internal randomness, but how does it hide its activity from, say, a security analyst watching the network? You mentioned the jitter.
Exactly. That's the really clever bit for operational stealth. When the worm pauses between actions like scanning or trying to connect, it doesn't just wait a fixed time, say 5 seconds.
It does what instead?
It injects jitter into that delay. And that jitter is calculated using the golden ratio, so you get these non-integer, slightly chaotic variations in timing.
Ah, so any tool looking for a regular rhythmic pattern like a heartbeat won't find one.
Precisely. It scrambles its timing footprint, makes time series analysis much, much harder.
Okay, so its timing is hidden. Let's talk architecture. How does it handle actually breaking in? The analysis suggests it's, well, pretty well built.
Oh, definitely. This looks like professional development. For example, they've addressed common vulnerabilities like predictable temporary file paths, that whole TOU race condition thing.
Where you can guess the file name between creation and use.
Right. They neutralized that during remote deployment by using cryptographically secure random suffixes for any temporary files. It's just clean, disciplined coding.
But then there's this concept they call controlled aggression. If it's so sophisticated, why wouldn't it just go full blast, try to spread as fast as possible?
Because full blast is noisy. It triggers alarms immediately. This worm is smarter than that. It actually throttles itself.
Throttles itself? How?
Inside its network discovery engine, it uses what looks like an asyncio, semaphore set to 20. So it strictly limits itself to only 20 concurrent outbound TCP connection attempts at any one time.
Only 20. That seems low.
It is low, intentionally. It prevents the worm from hogging system resources or creating that obvious high-volume scanning signature that network monitoring tools are built to catch. It's prioritizing stealth over speed, like a slow drip instead of a flood.
Okay, so a low and slow approach. How does it actually move laterally then? The vector is SSH, right?
Yes, asynchronous SSH, technically T1 tunnel 1.004. But it's not just brute forcing common passwords. It uses this really complex algorithm called permuta-dragon.
Permuta-dragon. What's that based on? Let me guess.
You got it. Rooted in chaotic powers of Filer that generates highly unpredictable, time-dependent credentials for each login attempt. The goal seems to be evading simple dictionary attack lockouts.
Wow. Okay, so chaotic timing dynamic credentials. This sounds really tough to stop with traditional tools.
It is, because the timing jitter bypasses time series analysis, and the credential forging bypasses simple signature or blacklist approaches. Your defense really has to be behavioral.
So what's the recommended countermeasure? What actually works?
The most effective thing. You have to shut down that SSH vector. The recommendation is clear. Enforce mandatory key-based authentication for all SSH services, everywhere.
Because if it can't use a password, the whole permuta-dragon credential forging thing is useless.
Exactly. It completely neutralizes that attack method. No password field, no attack.
Okay, but what about detecting it before it spreads? You mentioned it throttles itself. Can we use that?
Absolutely. That self-imposed limit, the 20 concurrent connections, that becomes its Achilles heel. We tune its stealth into a detection point.
Ow.
You implement security policies, specifically network flow monitoring, designed to spot that exact behavior. The recommendation is to flag any internal host that attempts more than 20 unique internal TCP connections within, say, a rolling 60-second window.
So you're basically setting a tripwire at its own speed limit.
Precisely. You use its own controlled aggression against it.
Okay, wrapping this up. What's the big picture here? The analysis mentions resilience, decentralized state synchronization.
Yeah, that's important. The different parts of the worm, the modules, seem to synchronize their state using complex methods like fractal Brownian motion. It means a whole swarm of these things could likely survive even if you find and kill individual infected nodes. It's built to be robust, decentralized.
Which leads us to a pretty challenging final thought for everyone listening.
Right. If sophisticated attackers are actively integrating things like pi and other nonlinear mathematical concepts into real-world cyber weapons, well, how much deeper does security need to go?
You mean we need to start integrating abstract math into our defenses just to keep up?
Maybe. You certainly can't fight these kinds of non-deterministic, chaotic threats using simple linear pattern matching anymore. It raises some big questions about the future of cybersecurity analysis.
Welcome to the deep dive. Today we're cracking open the source material on something pretty wild, the lambda text Ethereum pathogen core.
Yeah, it's quite something. We're talking about a network worm, highly evolved, asynchronous, built by an APT group with a deeply philosophical approach to their craft.
Right, and that philosophy is key. What really jumps out is this core feature, the golden ratio. They've baked it right into the worm's basic functions.
Exactly. It's the source of what the material calls its chaotic integrity. It's not just code, it's math driving the operation.
Okay, I have to stop on that. We read the lambda text Ethereum codex, this source document, and it talks about the worm as a digital poem seeking imagined total integration through eternal sovereign recursion. That sounds inefficient.
Well, yes and no. It sounds inefficient if you think speed is the only goal.
Which for most malware, it kinda is, right?
Yeah.
Get in, do the damage, get out.
Fast. True. But here, that philosophical mandate is the strategy. It forces them to use these chaotic phi-based algorithms instead of simpler, faster methods. They sacrifice speed deliberately for self.
So the poem part isn't just flair, it's functional. It makes it harder to detect because it's not acting predictably.
Precisely. If the timing and methods are fundamentally chaotic, rooted in Philida, how can standard security tools predict its next step? They can't build a stable signature.
Let's dig into the tech. How do they pull off this chaos? Architecturally, the sources point to a big shift to Python's asyncio framework.
Yeah, asyncio is the powerhouse here. It lets the worm handle, potentially thousands of tasks at once, scanning, probing without getting bogged down. Non-blocking I/O is crucial.
So it's juggling a lot, but the real evasion trick is this thing called feed jitter.
That's the core stealth mechanism, feed jitter. Instead of waiting a fixed time between network probes, like, say, every 5 seconds.
Which is easy to spot.
Exactly. Instead, they use the golden ratio to calculate the next wait time. It creates this dynamic, non-repeating pattern. It looks random, but it's structured randomness based on feeling.
So if you're watching the network traffic, you never see a simple, repetitive timing signature. Every pause is different, derived from philogel.
Right. And they don't stop there. They mix philoges with other mathematical constants, like philolog and etlers, to seed their cryptographic functions too. It ensures every probe attempt is statistically related but temporally unique.
Okay, wait. This sounds incredibly sophisticated for stealth, but then there's this contradiction, isn't there? The source code shows they use an asyncio, semaphore.
The throttle, yes.
They put a hard limit of only 20 simultaneous TCP connection attempts.
Yeah.
Why build this incredibly complex, potentially fast asynchronous engine and then slam the brakes on?
It's a calculated sacrifice. Speed for stealth. 20 connections is noisy, but it's often below the default threshold for basic network flow anomaly detection systems.
So they could go faster, but they choose not to stay under the radar.
Exactly. They'd rather move slowly and persist inside the network than blast out scans and get caught immediately. It's about longevity.
Okay, so stealth is paramount. Once they are inside, using this slow, chaotic approach, where do they go? What's the target for lateral movement?
The primary target, according to the material, is internal networks. Think 192.168.x.x, 10.x.x, and the main door they're trying to open is port 22, SSH.
Secure shell. Makes sense for deeper access. How do they get past authentication?
This is where Field comes back in again. They use something called dynamic credential forging, powered by an algorithm named Permuta-Dragon.
Permuta-Dragon.
Sounds dramatic. It uses high powers of filler, like filled cubed, fill squared, to generate unique, short, max 16 characters alphanumeric credential attempts. There's a very specific form of brute forcing.
And because it's based on filled and internal seeds, you can't easily predict the passwords they'll try.
Mathematically very difficult without knowing the exact internal state and sequence generated by the worm.
All right, so we have this stealthy, throttled, feely-driven worm targeting SSH. How do you fight that? Where do we start defensively?
The most direct counter. Shut down the main attack vector. make SSH password authentication impossible.
You mean enforce cryptographic key-based authentication only?
Absolutely, everywhere.
Please
If
don't.
SSH simply doesn't accept passwords, that whole Bermuda Dragon Feely-based credential forging attack becomes useless. It hits a brick wall.
Okay, that neuters the entry method.
Right.
What about detecting its presence, given the throttling? Can we use that limit against it?
Yes, that's the next step. Turn their strategic throttle into a detection signature. They limit themselves to 20 concurrent probes.
So you monitor for that specific number?
Precisely. Set up network flow monitoring. You need to flag any internal host that tries to make, say, more than 20 unique internal TCP connection attempts within a short window, like 60 seconds.
Targeting their self-imposed limit.
Yeah.
And you'd also look for failed SSH attempts.
Right. Add a rule for maybe more than 5 failed outbound SSH attempts in that same window. It targets both their reconnaissance and their brute force phase using their own constraints.
Clever. Okay, what about persistence? If it gets a foothold, how does it stay there and how do we kick it out?
It uses common techniques, but we can monitor for them. It likes to stage itself in temporary directories, like TeamB.
So file integrity monitoring, VM?
Yes, configure VM to specifically alert on any Python processes being executed from TP or similar ephemeral locations. That's highly suspicious.
And it probably uses scheduling to restart itself.
Cron tab is mentioned frequently in the sources, so process monitoring needs to be sharp. Watch for any unauthorized changes or additions to user or system cron tab files. That's their lifeline.
So summing this up, the core challenge here is that feel jitter timing. It makes traditional detection, the kind that looks for regular patterns over time, basically ineffective.
It really does. Standard time series analysis expect periodicity, or at least predictable intervals. This worm offers neither, thanks to feel.
Which leaves us with a crucial final thought, doesn't it?
Yeah.
For everyone listening, how do you adapt your security posture?
It means moving beyond just looking for what it does, the signatures of its tools, and focusing more on how it does it, specifically its timing. You need methods that can spot structure within chaos.
So not just standard anomaly detection, we're talking about needing specialized stochastic analysis, analyzing the probabilities, the randomness itself.
Exactly. Or maybe machine learning models specifically trained to recognize chaotic patterns that still have an underlying mathematical structure, like those derived from the golden ratio. It's about detecting the signature of chaos, not just a fixed action.
Spotting the ghost in the randomness. A very different kind of defense needed. Fascinating stuff.